This is Fundamentals of Micro and Nanofabrication. I am Swayam from IIT Bangalore, and today we are going to start a new module on subtractive manufacturing, specifically wet etching. So let's get started. So the first lecture is on figures of merit. Just like when we did deposition, we took 15 minutes to understand the various jargon and definitions that are used to define etching or deposition in that case. Similarly, we will take some time to understand the figures of merit of etching. So the four figures of merit that we shall discuss in this lecture are etching rate uniformity, anisotropy, and selectivity, and take a little bit of time to understand what each of these terms mean. So the first one is etching rate, and it is the easiest one to understand. So supposing you had a film of a certain thickness d0 and you want to etch this film and make it thinner. So you would put it under an etchant, whether dry or wet, and that etchant would eat away the material, and the film would become thinner. Now the rate at which the film becomes thinner is essentially called the etching rate. So strictly speaking, the way we define it, if in time t you are losing delta t of this material, then etching rate is nothing but delta t by t. Now etching rate, as you can imagine, is one of the most fundamental and simple things for any etching recipe, and must always be noted and must always be communicated. However, there are complications associated with etching rate, which we shall tackle in the next. So it turns out etching rate is not always uniform, and you can imagine there are several reasons why this could happen. It is possible that the etching solution itself has fundamental issues which prevent it from being uniform. A good example would be supposing an etching solution is not very ideal and tends to produce precipitates, which in that case the precipitate would form randomly or with different parts of the wafer, and different parts of the wafer would then be exposed to the etching solution at a different rate, which might lead to a difference in etching. But even if those fundamental issues are not there, even if the etching solution is pretty good, the etching solution has very good chemistry or very ideal chemistry, there are other things that can happen. For example, it is possible that the etching rate is dependent upon the feature size. So this often happens if the feature sizes are very small. So let's take an example. Supposing you had a silicon wafer, and let's focus first on a feature that is smaller. So there are three feature sizes shown. Let's, for argument's sake, say that this is a nanometer size feature. If this is a nanometer size feature, in order for this film to etch further, the etching solution must enter this hole, must wet this whole portion, and reach the substrate or the etching film. The film that you want to etch in order to perform the etching. And if this hole is very small, due to various effects such as surface tension, such as bubbles that might be forming or gas inclusions, etc., it is often hard for an etching solution or etching plasma to get in, and that leads to lower etching rates when you are dealing with smaller feature sizes. If all the features on your wafer were the same, then this would not be so much of a problem. It would mean that you have a lower etching rate, but at least that etching rate would be consistent across the wafer. But of course, in a real mask, in a real design, you have various different sizes, different devices with different opening areas, with different areas that are open, different patterns. And all of that heterogeneity means that an etching would often process at different etching rates. So if you come back to this figure, this is what I am trying to highlight. So supposing you take three different feature sizes. So some feature size that is fairly large, some feature size that is average, and some feature size that is small. If you go to if the unit process was developed for a certain feature size, supposing this is the feature size that it was developed, it might work very well for that feature size. However, for feature size that are smaller or feature size that are lower, you might get a different etching rate. There's also an effect of sample loading. It's a more complicated effect that we shall deal with when we talk about these etching solutions, especially in dry etch. But overall, what is happening is what is seen in this SEM. So you are doing dry etching here, and in this dry etching, you are doing very high aspect ratio etchings. This is an anisotropic etch. Anisotropy, high aspect ratios are words that you shall probably know more of in the next few slides. But for now, it is sufficient to imagine that you have these very deep holes that you are trying to etch. And depending upon what is the opening of the hole, depending upon what is the size of the hole, for the same length of etch, you actually get different depths. So holes that are larger get etched deeper, holes that are smaller don't get as deep. And as I mentioned, this can be complex effect. In this case, it is because of mass transport. So in order to do the etching, both the etchant must go in, and whatever the byproduct is being formed must go out. And it turns out that it's much harder to do these in these narrow, small opening area features than these large features. And that is why the etching rate is smaller in these features, but higher in large features. The second thing you want to do in order to get uniformity is that you want extreme sensitivity to temperature or agitation. A lot of etching solutions are exothermic, a lot of etching solutions are endothermic. Some of the etching solutions need to be heated through an external heater, and all of these things mean that the temperature can never strictly be kept uniform. So etching solutions or etching recipes that are extremely sensitive to temperature, require extremely high uniformity, are often not ideal. The same thing with agitation. If you remember that during CVD we talked about diffusion through a boundary layer of how etchant needs to get in, the precursor needs to get in and the byproducts must get out. Something very similar happens even when you do etching. In this case, the etchant must get in and the byproducts must get out. And if it's just a static solution, then you are just depending on diffusion to do this process, but that can sometimes be non-ideal. So you want to have some sort of an agitation. However, if the agitation by its definition is non-uniform and that affects your etching rate, then that is also not good. So you have this various sort of optimizations that you want to do, where your etching solution should not be very aggressive or should not be too passive, right? In reality, there is really no ideal etchant. All etchants have some level of non-uniformity. The trick is to characterize that non-uniformity, and the trick is to precisely to characterize it enough so that an engineer can design around it. Okay. So in general, dry etches tend to be a little more non-uniform than wet etches. This is an example of a dry etch being more non-uniform. Deep etches tend to be more non-uniform than shallow etches. Again, a good example. So if you are trying to do very narrow but deep etches, then the etches that need to go very deep tend to be a little more non-uniform than etches that need to go shallow. And typically, fast etches are much more non-uniform than slow etches, and this comes back to the ability to control. Something that happens very fast is very hard to control. Something that happens a little more slower is often easier to control. Now, typically when you design an etching recipe or perform an etching experiment, you start with a nominal etching time. So supposing you were to etch a film of 100 nanometers and the process engineer told you that here is an etching solution that etches at 10 nanometers a second. So you know that in order to etch the 100 nanometer film, you need to put the film in the etchant for 10 seconds, right? But that is just the nominal etching rate. Because of non-uniformity, now you have to do some compensation, because the actual etching time is not exactly 10 seconds, it is 10 seconds plus minus whatever the non-uniformity is. In the worst case, you would have an etching rate that is slightly lower than nominal, but you would also have some non-uniformity associated with the film. So when you did the deposition, you had a nominal deposition rate, but that deposition rate was also not exactly uniform. So you have to, when you are calculating the etching time, you also have to remember that that film might also be non-uniform. So not only is the etching time varying, but also the thickness of the film being etched is also varying because it is non-uniform. So both of these must be accounted for to calculate the worst case etching time. The time that you must put the film, you must do the etch to make sure that all the features on the film are at least getting etched to that required depth. So here is the math behind what I just said. So supposing you were trying to do etching, and the nominal etching rate is RF, but then it comes with some non-uniformity, and say it comes with a non-uniformity of phi f, which is plus minus phi f. In the worst case scenario, your etching rate will be slower than RF. So the etching rate RF minimum is nothing but RF into 1 minus phi f. So this is the variation factor. Also, you have a variation in the film thickness. So nominally you have a film that is DF thick, however, it's also non-uniform. So in the worst case, the thickest film that you will encounter is not at DF max, which is equal to DF into 1 plus delta, where delta is a variation of the deposition. This is the variation of the film thickness. And this allows you to calculate your worst case etching time, right? This is a time this is the time you need to ensure that every area on your wafer has etched to at least the target depth. So that absolute worst case etching time is nothing but df max, which is the thickest film you can have, and the rf min, which is the slowest etching rate you can have, which is equal to the nominal etch rate multiplied by 1 plus delta, where delta is the variation in the thickness, and 1 minus phi f, phi f is variation in the etching rate. Point of this whole argument is always be sensitive to variations that can occur. So when you are chaining processes together, you must also remember that variations also chain together. When the deposition is the first step, you only have to worry about deposition uniformity, but by the time you come to etching, you have to start worrying about the uniformity of all the processes that preceded the etching in order to really ensure you get a good yield. The next, we have to understand anisotropic and isotropic etches. So here are some examples. So let's start with the simplest one, which is the isotropic etch. So here is your etched film, and it has a certain pattern on it, and this is what this masking layer looks like. How to make mask has already been covered in photoresist in the module on lithography. Now, the design has an opening that is wide from this point to this point. So these dotted line represents the design opening size. Let me actually grab my pointer real quick. However, what you actually get is slightly wider than that. So supposing you were etching a certain depth d, you would go in the vertical direction a certain depth d, but if it's an isotropic etch, which means it etches in all the directions equally, then it would not just etch in the depth, it would also etch laterally. So it would also etch in the lateral direction. So it will etch under the mask and go left and go right. Now I have shown here the extreme case where it's completely isotropic, so the depth it etches to and the lateral width it etches to is exactly the same. But this is an exaggeration, that doesn't always happen, but it's still indicative of what can happen. Now this does two things. Number one, it makes the opening that you actually get slightly wider than the opening that you had designed it for. Now this becomes problematic for films that are for etching depths that are either too thick or for openings that are too small. So any time your opening becomes the same size as your etching depth, you need to start worrying about the impact that that isotropic etches will start having on your feature sizes. Often if you can characterize what this lateral etch is, then you can compensate for it in your design itself. The other case is the anisotropic etch, and the extreme example of it is given on the right hand side. So in this case, you have your silicon film, you have your pattern on the top. These dotted lines represent the opening that is the intended opening, the design opening. And when you do the etch is exactly vertical. It etches in the vertical direction, but there is absolutely no etch in the lateral direction. Now this is the completely 100% anisotropic etch. Anisotropic, the words itself suggested it's not isotropic, which means it's not equal in all directions. Of course, reality is somewhere in the middle. Often etches have some amount of anisotropy. So what you actually get is either some sort of a slope. It doesn't have to be a linear slope. Sometimes this is a complex polynomial slope. But some amount of under etch and some amount of slope. So you don't ever get 90 degrees, you don't ever get exact spherical or hemispherical, you get somewhere in the middle. Often etches that give you profile that look like these are called anisotropic etches, okay? And profiles that look like this are all called isotropic etches. Of course, there are differences, but in general, wet etches where you're using a liquid chemical, they tend to be isotropic. Dry etches where you are using plasma, they tend to be anisotropic. Now in general, whenever you are doing wet etching, which is that you are taking an etchant that is liquid, you tend to be isotropic. And in general, when you are doing dry etching, which is when you are doing the etching using plasma, you tend to be anisotropic. Now of course, there are slightly exceptions. You can get wet etches that are anisotropic, and you can get dry etching recipes that are isotropic, but those are details that we shall discuss when we come to them. The second thing we have to sort of understand right now is things that tend to make recipes isotropic and things that tend to make recipes anisotropic. Now So I urge you to remember the lectures on diffusion, where we had two cases, right, where the film, the etchant solution, sorry, the deposition precursor was coming in, it was diffusing through a boundary layer, it was getting to the surface and doing a reaction. And we had talked about how these two flux, the diffusion flux and the reactant flux, have to be in balance. And that led to the two different regimes where the deposition reaction could either be diffusion limited or mass transport limited, or could be surface reaction limited. Etching is essentially deposition process in reverse, by which I shall not go into excruciating detail like we did in CVD to completely understand the process. Very frankly speaking with you, the process is not as well understood, but the basics still apply. So you can either be limited by the diffusion through the boundary layer or through the stagnant layer of the etching solution, or the reaction could be limited by the surface reaction. And depending upon which of these is the limiting factor, the etches tend to be isotropic or anisotropic. Typically, diffusion limited etchings tend to be isotropic, and this is not hard to understand because diffusion as a process is completely direction agnostic. If it diffuses in the vertical direction, it will also diffuse in the lateral direction, and you would probably get the same etching rate, which would give you an isotropic etch. However, chemicals that are surface reaction limited can have a directional dependence because different facets of the crystal may etch at different rates, they have different surface energies, and that might lead to a change in etching rate. So, reaction rate limited regime often makes etches anisotropic. Some of the very aggressive chemicals that have very rapid reaction rate tend to be isotropic, and the reason for that is if the reaction rate is very fast, then often if the surface reaction rate is very fast, then often the reaction is limited by diffusion, right. So, you are always limited by the slow step. So, if the reaction rate is very fast, you are limited by diffusion, which once again means your etches will be non-directional because they are diffusion limited. Mild etchants which have a very low reaction rate, the reaction rate tends to be the bottleneck, diffusion is not the bottleneck, and if the reaction rate is bottleneck, it has a possibility of being anisotropic. Often concentrated and viscous etchants. Now, these are etchants where diffusion is very slow, and if diffusion is slow, then once again you are diffusion limited, and that tends to make etches isotropic. While dilute etchants where diffusion is not a problem, where surface reaction rate is the problem, they tend to often be anisotropic etches. Now, these are just thumb rules. Details are fairly complicated, but it's a good place to start. The anisotropy, or the presence of anisotropy, and the difference in opening of the actual hole that you etch and the intended size of the hole that you wanted to etch, it leads to the concept of under etch. So, you have sort of seen this already in the previous slide. So, you have a mask, you have a wafer, and you are trying to etch a film. Your intended, the dimension of the opening you wanted to have is say twice of dm, right. So, dm is half of the opening that you intended to have. But because of anisotropy or some level of anisotropy, some level of isotropic etch, you will actually get more than dm, right, because the etchant will not just etch vertically but also etch laterally. So, supposing you got df. So, in that case, the undercut that you would report, which is simply the difference of these two parameters, which is the distance from this edge to this edge. So, for isotropic edge, the undercut is large. For very, very anisotropic etch, the undercut is 0, right. And for all practical cases in the middle, the undercut is somewhere in the middle. Now, the effect of the undercut can be slightly different depending upon the pattern that you have. So, here is a case where undercut increased the size of your etching hole. However, if you are trying to not cut a hole, but you are trying to make a pillar, right. In that case, the undercut would actually decrease the diameter of the pillar instead of increasing the diameter of the pillar. So, this is what I am trying to highlight in the figure here. So, once again you are undercutting in the sense you are laterally etching in, but because of the lateral etching in, instead of having a pillar of radius dm, you are actually getting a pillar of radius df. So, this is the same concept, it is just that the actual effect depends upon whether you are trying to make pillars or holes. Now, the third figure of merit that is often reported for etching solutions is the degree of anisotropy. It's related to undercut, but strictly speaking what it tells you is that you measure a lateral etch rate, which is the etching rate in the x direction, and you measure vertical etch rate, which is the etching rate in the y direction, and you simply calculate how different are they from each other. So, you calculate a parameter called AF, which is equal to 1 minus the lateral etch rate divided by the vertical etch rate. Now, if the solution is exactly isotropic, then the lateral etch rate would be equal to the vertical etch rate and the value of A would be 0. So, 0 degree of anisotropy means the film is exactly isotropic. If on the other extreme case your lateral etch rate is 0, then in that case the value of this parameter AF is 1, which is the case of exactly anisotropy, exactly an isotropic etch, completely anisotropic etch. The real world, which is in the middle of this 0 and 1, tells you how anisotropic your etch really is. The fourth and a very important parameter for an etching recipe is selectivity. So, in general, when you are doing an etch, you are not just doing an etch on a blanket film. Often you are doing the etch with a pattern already on there. So, supposing you are etching this grey film, that you would have some masking pattern, which is this orange photoresist, right. Now, when you are etching the film that you want to etch, the same etching solution can also etch the mask a little bit, right. Now, the degree of at which it etches the mask versus the degree at which it etches the film that you want to etch is called selectivity. So, mathematically selectivity between is a function of both A and B, where A is the film you want to etch and B is the mask. So, selectivity between A and B is nothing but the etching rate of the film divided by the etching rate of the mask. If the etching rate of the mask is 0, then selectivity is infinity, which basically means that you are not etching the mask at all, you are only etching the film, which is the ideal case. In general, you always are etching the mask, maybe at a slower rate, but you are always etching the mask to some extent. So, the selectivity falls. Selectivity can actually is equal to 1 if the etching rate of the mask and the etching rate of film are equal. Now, you would think that that would be that is a worthless etch, but it's not really, because you can always that simply means that the maximum etching depth that you can realistically achieve is equal to the thickness of the mask, right. So, supposing your mask thickness was 1 micron and your selectivity is 1, then the maximum hole you can possibly drill or possibly etch using etching is 1 micron. Right? If, however, your selectivity is 100, then for a 1 micron thick mask, the maximum hole that you can etch is 100 micron. If your selectivity is 10,000, then given 1 micron, you can etch 10,000 microns. So, that is why the selectivity becomes very important. It tells you the maximum amount you can etch and still get a feature. In some extreme cases, the selectivity actually can be less than 1. That simply means that you have to put in a lot more mask to get a certain etching depth. This often is the case for materials that are very hard to etch. For example, some oxides, some very stable, some noble metals. In those cases, the selectivity can even fall below 1. Okay. What does the selectivity depend upon? It of course depends on the chemistry. What is the material of mask A, what masking material, what is the material that you want to etch. An acid would attack a metal very fast, but the acid may not attack a polymer that fast. So, polymer might so against polymer and metal, the selectivity would be very high with the acid. However, a base can attack both organics as well as some metals, so the selectivity there would not be very good. It also depends on concentration. Dilute solutions tend to be a little more selective, or concentrated solutions tend to be little less selective. And temperature, typically low temperature you get a little better selectivity. At high temperature virtually everything starts etching and then you get lower selectivity. But those are thumb rules, you always need to look at the details. With that, we come to the end of the lecture on figures of merit. In the next lecture, we shall get into the basics of etching and look at some chemistries, some actual recipes of etching. Thank you.